All right, so I should have your homework 2 or math packets. If I don't, then either submit them before the end of class or turn them in on Canvas, or you could leave them in the box outside of my office, as you prefer. So while people are coming up, I will pull up the slides, and the plan is we're going to go over the load factor, which I forgot to mention the last time. We're going to answer any questions you may have had after starting to work on it a bit. And then the plan is we're going to have time I have the chapter 3 packets. And so we're just going to spend class time thinking about interesting problems and trying to solve them. I've got markers, so we'll put our answers up on the board and compare. And then at least I plan for like 2:30 to be our work time. So you can get in your groups and talk with each other and continue to work on your project while I'm here available for any questions. Sounds good? Okay. Let's go to the right place. Okay, so we talked about hashing, and this is the part that I forgot to mention last time, where, just to remind you, a hash is some function that we have some key and it gets mapped to something secret that obscures it. Typically we map it to an integer, and then we put this item into that integer spot in our array, typically. So one of the issues with hashes are, what if two things have the same hash? That's called a collision. And so one way of fixing it is to use a linked list and do chaining, where here's my original array, and then for each thing that hashes to that value, I've got the head of a linked list. And so like 7's got many things that hash to 7, and so I just chain them like this. So kind of like if I'm holding something out and I just add like paper chains down here, that's for each item that hashes to that value. Another way of collision resolution is probing, where you start off where it's supposed to be, and then if there's something already there, you just go to the next available spot to find out until you find the available spot and you put it there. Right, so that's collision. The hash table, especially if we implement it with arrays, tend to have fixed size. So like if we have n items and m buckets, where each of these spots in the array, that's the bucket. And so there's a point where maybe we're inserting so many things and there's collisions happening, and so the table's starting to get kind of full. So we need to do a process similar to reallocation, to just have more space than copy everything over. So the hash table, when it's fixed size, we need to keep track of how full it is. Yeah.
Are we gonna go over a space complexity?
Space complexity. That's a good idea. Hadn't planned on it, but yeah, if you let me think about that. If you
It's like pretty similar to space complexity.
Yeah, so time complexity is like when we're looking at an algorithm, how much time is it going to take in the worst case, best case, average case? Space complexity is calculated similar, where instead you're not looking at the steps of the algorithm, but you're considering how much space is needed to execute this algorithm. So for like what is it, like merge sort, where you need extra space, where you need like extra arrays to split everything up, that has a higher space complexity than just like sorting everything in place, where you don't need any extra room. if you have specific questions as we go, I'm happy to take a stab at those.
Thank you.
Um, okay, so we need to keep track of how full the hash table is. We do that with something called the load factor, which is typically represented as the Greek letter alpha, but it's just a simple ratio of n over m, where n is the size of our data, the number of entries that we've got, and m is the number of buckets. So what's our capacity? So for this one, if we inserted 44, then it's n is 1, 2, 3, 4, 5, and m is 12. And so then you as the designer can say, at what point do I want to rehash? At what point do I want to have more space? And so you are in charge of designing how full you want it to get. So you set some alpha max, maybe 0.6, 0.7, up to you. And then you resize or you rehash when it gets too big. And so that, since the hashing function, you've got some, let's go over here. So you've got some function mod the number of buckets. And so you would need to, you can keep the function the same, but the mod will be different if you have more buckets. So you just need to rehash all your new things. Yeah, so that's like why we call it rehashing, because you have to compute this function again with a different mod. You can also decide to rehash if it gets too small. So maybe when you're max over 4, and then you're like, okay, I don't have enough entries in my table to warrant having a table this big, so let's downsize. That's also a consideration for rehashing. It also may depend on your method of collision resolution. If you don't have many collisions, or if you're doing probing, then maybe you would want to rehash sooner than if you're doing chaining. So there's a lot of decision factors that go into this. But there probably is a point where you need to reallocate and make more space. Okay, that's all I wanted to mention. Something you should know about hash tables. Are there any questions about your data structure in general that you think the class would benefit from? If you started talking with your group and you're like, I don't know what's going on here. Okay, hearing none. Then we'll just go on to the packet. And so I think what I'm gonna do, I'll probably pause the recording. And so we'll spend time in groups talking about it. And then when we go to discuss it, I'll start recording again and summarize what we did. So the Zoom recording for this will be fairly boring. But the point of the class time now is just we know the basics of these data structures. Let's practice and do some interesting problems. Okay, so get in your usual groups as you would like. I'll go through and pass some markers around, talk about the problems, and then once you have an idea, put it up on the board. And for those of you on Zoom, you should have access to the packet on Canvas, and so you can just work on those. So what do you think? So the idea for this is that all of these push, pop, and find min should be constant. And the thing with it being constant, if we've got 1 and then a million numbers bigger than 1 on top of it, we don't want to have to go through the whole stack find one and then be like, I found it. I found one. It's the minimum. I still had to go through, that's order N, right? To go through the whole stack. So I don't want that to happen. So what do you think I should do? We know how push works. We know how pop works. So all we need to do is elaborate on how do we find the minimum. Yeah. What do you think?
Um, at first, I probably just had like one like, conditional for push or pop.
Mm-hmm.
But then if you pop and it's the minimum, you have to find the minimum. So I was thinking you might have to have like a separate stack for the minimum. So you have like a runner up. You get rid of them up, so having to search the whole way to keep it constant time.
Okay. So as you push, you keep it, because then you still have the same problem. Or like, how do you store the things?
Sort of.
Yeah. Okay.
I don't think this is the right answer, but like just when you're adding stuff, just when you have a minimum variable and then when you're adding stuff to the stack, just switch just if it's when you're adding is less than your minimum variable, just reassign that, just set a minimum variable to that.
Mhm.
There's always that having.
Yeah, so that's the idea with for push, where you so if we're pushing X, we check if S is less than the min. And then if it is, then now we've got the minimum variable. But then the problem comes with pop, with what happens when we pop our minimum variable or minimum value.
But what was wrong with using the stack?
So in what way were you gonna use the stack for storing?
Because like if you're using, because like having like a nested push, so like to having you push into the original stack and you have like a stack for like the minimums that you impact to if the conditionals is met. Then you kind of then if you access if you it would be a stack. Yeah, because then if like the least one and then you just pop that one out of the link stack, that's also a constant time operation. It's two constant time operations.
Right, so my concern is the min stack of how do you know that my concern is the min stack in the order, like A, how do you know to push something to the min stack?
But if it passes it passes the condition.
And what's the conditional?
Yeah, if it's less than then it comes to the new term. The previous minimum comes back when it back to
Okay, so let's try. So let's say I have 1, 3, 2. Actually, let's make this um okay, so let's push all of these things and pop here and see if it works. So this is our main and over here is our min. So if we push 1 and then we've got a box for the min, currently 1. And then we push 3, min doesn't change. Then we push 2, min doesn't change. And then we pop. Min hasn't changed. Oh wait. I don't like this example. I want a situation where we pop the minimum to actually figure it out. Okay, let's.
Numbers like one, a low number, higher number, low number.
Lower number, higher number, lower number. Okay, so let's say. Do you have number examples?
I've been trying to think.
So if we have a higher number and then maybe let's say we push 5 first. 5 is our min. And then we push 3. 3 is less than 5. 3 becomes our new min. Then what do we do with 5?
Yeah, I mean, 4 is gonna give us, it skips.
And then we add 10. That's fine. And then if we add 4, that's great. But if we No, I think that might work. Yeah, I think that works because even if we pop 4, then it doesn't matter anymore. The only issue is once we pop 3. And if we've saved our old minimum value here,
Is it the, is it not, I mean, is it not the most like space efficient? Like,
right, so it's constant time in terms of runtime, but it's what's the situation? If we had, I think the situation is like decreasing numbers, like 10, 9, 8, 7, 6. That's would be the space complexity then would be n, because if we had, so first 10's our min, and then 9. Now 9's our min, we add 10 to there. And now 8's our min, we add 9 there. And so the worst case is if we are getting decreasing values, then the min stack is going to be like, yeah, like copy minus the newest value. So I think that works, of having a min stack. So, okay, so if this was on an exam, what would I ask you to do? Whoops. So on an exam, maybe I would write have a min variable. Reassign to it during push if the new thing is less than whatever is currently there. So that takes care of this one. And then have a min stack. So we've taken care of push. So when we're adding something, what's there? So now we have to take care of pop. So if our min is popped. Oh wait, we need to. So we reassign the min variable when we push. But when we reassign, we have to save the old one. So if there is an existing old min, then we push it to the min stack. So then if our min is popped, then we can pop from that stack to get the old one back. And so then so this is great having a plan, and then I would try and include like some sort of drawing like this of here's a sequence of numbers and here's what happens if I pop some, to show kind of visually that it's working. If you think of the worst case, like this 109876, then I would also include that of this is the worst case where the min stack would like fill up as we insert everything. Yeah, really like that. Does anybody else have a different approach? Yeah.
Like make a list, like a separate list of all the elements in the stack. I don't know what that is.
List of stack elements and find min of the list. Are we talking about like storing the stack as a list?
Yeah.
I think that works, but I think also finding the min of a list can be order n. Because we'd have to go through the list. And so that's not necessarily constant time. Right, so having this min variable, because we have this value ready to go, it's constant when we query it. It's just a matter of updating. And so so I would argue that now, even though we've a little bit modified how push and pop work, they're still constant because it's just a matter of doing some conditionals, which we assume takes no time at all, reassigning a variable, which we assume takes no time at all, or pushing to a stack, which is constant time. And then pop just adds another step of popping from min stack. So since it's not a function of how much data we have, it's just like one value, that's what makes it constant time. And if you say something like that, then that would be good too. Just to argue that like you've got your design here, and so just to emphasize, it really does run in constant time. Here's why.
The question I said, base stack one and two stack.
Yeah, that's a good question. Design A stack S. Here's the thing about abstract data types. It can be whatever we want it to be. So technically we've got a stack, like if this is our stack S, it's kind of this amorphous blob that we can be like, this is the real stack we care about. And we've got other things over here that help us do this. But like this is the main data structure. And that's got push and pop. And then we've just got a secondary stack over here that helps us out. But like this, all of these things as a whole make our data structure. Other questions? Cool. All right, and I'll make sure to post this on Canvas as well as we go. So next question, discuss in your in your table groups of if we want to keep a refrigerator to minimize food spoilage, what data structure do we use? How does it work? All right, let's talk about number 2. So this one, I'm expecting there to be multiple different answers because the thing with designing a data structure is as long as you as long as you get all of the requirements, then it's technically acceptable. The only question is how efficient is it at what it does? So maybe the version you've designed gets the job done, but someone else has a way that makes it more efficient. And so in that case, we would go with the other version, even though both are technically correct. So let's kind of, I don't know, does anyone want to start with what they thought of, and then other people can bring up their variations? Yeah.
I'll do a priority queue. And I'll assign a higher priority, like I would just use the best by date. And then each day would be like. And so something's gonna spoil in like 10 days, do a priority of 10, it's like lettuce, that's gonna spoil in like 3 days. Put a priority of 3, and then lower the number, the higher the priority.
Mhm. Okay. Yeah, that makes sense. And so priority queue is better than just a regular queue. Why? Like what's wrong? Like if I buy milk at the store today and I put it in the fridge versus when I go next week, if I've still got milk left over and I put it in the queue behind my milk, that is or just a regular queue, that's fine. What's the benefit of a priority queue? Yeah. So I think that so you know how at the grocery store there's always like if I buy milk today with like the farthest code date, but if I buy milk like tomorrow with the soonest code date, then the milk I buy tomorrow would preempt the one I buy today. Right? If I buy milk today with um let's say like March 1st, but if I buy milk tomorrow that's that day, then this milk would need to preempt that one. Yeah, so that's the point of the priority queue. That's the question I was asking of why not just a regular queue? Yeah. Any variations anybody did? Any other considerations that you took into account? Yeah.
Um. Actually, well, I was thinking, about if you have like a produce, it doesn't necessarily have like like a Best Buy bid. I don't know, I think it might be kind of redundant, but hypothetically, had like a really big fridge, I just have a separate queue for each item.
So like and so yeah, so with produce it gets tricky because there's nothing official. And so the same things could happen. Like you buy a good looking apple today and then one that's about to go bad tomorrow. And so you would need to eat that one first. So maybe you can like, if you, when you buy it, you're being like, this is going to last for 3 days. And that's the value that you associate with its priority. So like you have to do some work for things without a date added in. Anything else that you took into account? Other variations that you thought of? Okay, cool. All right, number 3. So tic-tac-toe is a game typically played on like a 3x3 board. 1, 2, 3, and 1, 2, 3, where 2 players take turns. So maybe player 1 puts an X there, player 2 puts an O there, and so on. I hope you know how to play tic-tac-toe. And the game's won if n consecutive, so in this case 3 consecutive X marks are placed in a row or a column or a diagonal. And so your job is to create a data structure with order n space that accepts this sequence of moves and reports in constant time whether the last move that was played won the game or not. All right, go for it. So this is a hard problem. I didn't come here with an answer for this, and so we're all thinking about this together. So, yeah.
So our idea was just rearrange, so you have an array for, an array of type n, two arrays of type n and one array of type two. So the base complexity would be 2n plus 2. And then so each array like corresponds to given line. So you have a columns array, you have a rows array, and then a diagonal array. And whenever you put a figure down or like a marker down, you update um the all the spots associated with it. So if you put a X in the top left, for example, you would add plus 1 to the column array, application 0, the rows array 0, the diagonal array 0. And then if you add a 0, then you subtract, or you add an O, then you subtract. And then you know if you ever reach, if you ever reach n or negative n, and then somebody will.
Okay, so play. Okay. Okay, so let's number them 0, 1, 2 because we're programmers. Okay, so X goes in 0, 1. Where do I put O?
So if you have exposed X, then in your columns array, the index 1 would go to 1, or you would increase it by 1.
Oh, yeah, okay, yeah,
And everything is sort of 0.
okay.
Rows array, that go to 1. And then it's not intersecting that diagonal, so you don't have to update anything else.
Okay, so we've put an X 0, 1. Play tic-tac-toe. So an O went in 1, 2. So where do I put it in columns?
Now at columns 2, you put negative 1.
So X implies add 1, O implies -1.
Yeah.
So then what do I do in rows?
Oh, 1.
Okay, and then diagonal? Okay. Let's do something on the diagonal. So X is in 1, 1, so column 1, you add 1?
Yeah.
And row 1, add 1? So now that's 0?
Yeah.
And then diagonal,
Oh.
Wait,
Sorry.
is this the diagonal array?
Yeah, the data.
Okay. Okay,
Say that both of diagonals are +1.
I'm interested to know how the size, what the size of the diagonal scales to as n increases. That's a side note. I would like to know that. That sounds right, but I would like to know for sure. Anyway, let's continue. Okay, so let's say X wins now. Wait, no, O didn't play. O's gotta play. If O blocks, then column 1 gets reduced by 1. Now it's just 1. Row 2 gets reduced by 1. Nothing happens to diagonal. Okay, so now I actually do want to make X win. So if I put X in top right, column 2 is now 0.
Yes.
And row 0 is 2. Ah. Diagonal. So maybe we just
Yeah.
like assign an orientation to one of them. So if we say that's the case, then this is 2. And then if O isn't paying attention, now O is column 2, -1. Right, column 2. Row 2, -2. Diagonal 0. And then X wins, hooray. So that's column 0, which is 1. Row 2, which is -1. And diagonal 3. And now, since it's 3, the goal is for X to get to 3 or O to get to -3. Yeah. Never more than 3 spots you have to check when the move is played. Why is that?
Like no matter how big the board is, you're always gonna have at most one column, one row, and then if you get a bad row, you also on a diagonal. So every time I'm just like going up to check those three, just to get people.
So row, column, or diagonal. Right, but I like, what if the game is 1,000 by 1,000?
That's. Like the diagonal at first, like I was thinking you put a full table and you're counting like 3 in a row for the full table. But since it's like specified that you have to get n moves like in a row next to each other, there's only gonna be 2 diagonals possible for each side of the board.
Yeah, because like, I mean, that makes intuitive sense. Like the only diagonal possible is here. If you choose like something along there, then that's not gonna be N. Okay, so I'm confident in that. Maybe I would like a more formal proof, but that makes sense to me. Okay, I do want to have time, sorry, it's not 2:30, it's 2:50. But I do want to have time to go over the groups, and I know there are other tic-tac-toe implementations that you guys have been working very hard on. So next time, we'll maybe recap this, come at it fresh and see, does it still make sense? Is there anything that we may have missed? Which happens a lot to me when I'm like working on a solution, then I come back to it and I'm like, why? This doesn't make sense. So we'll try this again on Tuesday, and then we'll keep going on the worksheet. So I hope these problems are fun so far. So yeah, so now it's time for you to get in your groups and chat about things, start planning things out, and I'm here to answer questions until 3:10 or so.